All right, let's go ahead and get started. We're going to be talking in this video about the history of the atom, or I guess more specifically, we're going to be talking about the series of events and the individuals who were instrumental in helping us to understand the modern idea of what an atom is. Remember, we can't see atoms, so we have to rely on experimentation to help us to understand this basic particle of matter. What do we believe today to be the basic particle of matter, the thing that we call the atom? So we're going to start with an individual who lived in ancient Greece whose name was Democritus. And Democritus lived 450 BC. He was born in an area of Greece known as Thrace. He was a very wealthy individual. He inherited vast wealth from his merchant father, and he used this wealth to satisfy his curiosity about the world. We know he traveled to Europe. He probably made his way all the way to Asia, but eventually he came back. He came back to Athens, and while there, he developed an interest in mathematics and in particular geometry, but also in science. And he asked a very important question, and the question was, what is the fundamental unit of all of matter? And his conclusions were based not so much on scientific observation, because there was no such thing as a scientific theory at that time. There were no experiments, but it was based on simply instinct. And what Democritus came to believe was that all atoms or all matter was based on a particle, a fundamental particle, which he called atomos, or indivisible. That's what that means, atomos, indivisible. So according to Democritus, everything in the universe was made of particles which were indivisible, which he called atomos. So a unit of matter might have been something like this sphere. So you can't divide that sphere anymore according to Democritus. But he did say this, that the particles were different for different substances. They were basically the same. They were essentially like a sphere, but they had different shapes and sizes. So, for example, the particles that made up water were essentially very smooth, and that smoothness was conferred onto water itself, so that the water that you drank, or the water that was flowing in the streams, was able to flow because the particles that made up the water were spherical and smooth, as opposed to, say, iron. So if you look at an iron bar or you look at an anvil, the iron that makes these things up is very solid and very rough because, according to Democritus, the atoms were they may have had little hooks on them. So again, Democritus' idea of the atom was that they were basically the same from atom to atom, but they had minor differences. Some were a little smaller, some were a little larger, and they had minor differences depending on the materials that they made up. Now, in 1804, John Dalton comes along, and he's an English scientist. He's a brilliant individual, and as a matter of fact, he was a Quaker that started a school. At the age of about 13 or 14, he joins his brother, and he decides to study science and mathematics. And that led him to a series of experiments that made him rethink this idea of the atom. And he came up with a number of postulates that made him believe that the basic unit of all matter was, as Democritus had surmised, was the atom, but with a few minor differences. For example, he again said that elements are made of extremely small particles. He calls them atoms. Democritus calls them atomos, but essentially the same thing. But he goes on to say that atoms of a given element are identical in size, mass, and other properties. In other words, the atoms of silver are different than the atoms of sulfur, that are different than the atoms of gold, and so forth. Atoms of different elements, different in size, mass, and other properties. So all of the atoms of one type are like those types of atoms, but very different from all of the types of atoms. And he says, thirdly, atoms can't be created, or subdivided, created, or destroyed. This was an idea presented by an individual named Louis Lavoisier, a Frenchman, who came up with this idea of conservation of mass. But yet another piece of the puzzle that helped Dalton to understand that the atom was the basic unit of all of matter. Dalton goes on to say that atoms of different elements combine in simple whole number ratios to form chemical compounds. simple whole number ratios. This was the law of multiple proportions. In other words, atoms, if they combine in multiple ways, combine simply, never with complicated or even fractions, but with simple whole number ratios. And finally, number 5, in chemical reactions, atoms are combined, separated, or rearranged. So again, all of these evidences taken together indicate a fundamental unit of nature called the atom. In 1897, J.J. Thomson comes along, and he is interested in a special type of radiation called what he believed to be radiation, which he calls cathode rays. And what he does is he studies these cathode rays in a particular tube called a cathode ray tube. And these cathode ray tubes were designed specifically to allow these cathode rays to flow from one part to the other. And here's a picture of the cathode ray right here. But what J.J. Thomson discovered was that if he placed plates below and above the cathode ray as it moved from left to right through the cathode ray, what happened was that the cathode ray was deflected away from the negative plate. That indicated to him that the cathode ray was negatively charged. Now, if that were true, that would mean it's not energy at all, it's a particle. It's a particle, because it would not have been deflected had it been simply an electrical wave. So he deduces then that this particle is negatively charged, but what was most important was that by the deflection, he was able to calculate roughly the size of this particle. He finds that the particle is smaller, not just smaller, but much smaller than the atom. And from this finding, he contradicts Dalton. He says that Dalton is wrong in saying that the atom is the basic unit of matter, that in fact the electron is smaller than the atom, and it is much smaller than the atom. And he comes up with this model of the atom, which he calls the plum pudding model. Now, the plum pudding model is attributed to J.J. Thomson, and essentially it says that the electrons are embedded throughout the atom like plums in a plum pudding. All right, Ernest Rutherford was an early student of J.J. Thomson. He worked in the laboratory of J.J. Thomson, and he did an ingenious experiment in the laboratory of J.J. Thomson using gold foil. So it's called the gold foil experiment. And what he said was that alpha particles, which are essentially helium nuclei, in other words, helium atoms without the electrons, when shot into a piece of gold foil, would usually pass straight through, which is what you would have expected, which he would have expected if the gold atoms were simply electrons embedded throughout the atom like plums in a plum pudding. But what he found was that occasionally these alpha particles would deflect, sometimes at very great angles. So that indicated to him that the gold atoms had a very, very dense nucleus, very small, very small. He used the analogy of a fly in a cathedral, but very dense. And J.J. Thomson then is credited with the discovery of the proton, Now, sometime later, an individual whose name is Millikan uses an apparatus which he calls the oil drop experiment to calculate the exact mass of the electron, and what he finds confirms the finding of J.J. Thomson that the electron is very, very small, about 1/2000th the size of the atom. So Millikan then is credited with helping to determine the exact size of the electron. In about 1916, an individual whose name is Niels Bohr comes along, and Niels Bohr is a mathematician essentially, and he calculates the trajectories of these electrons. And he says that the electrons are particles small particles, but they're not simply suspended in the atom as J.J. Thomson or Rutherford may have believed, but instead they're orbiting the nucleus like planets around the sun. And sometime later, in the early 1920s, an individual whose name is Erwin Schrödinger comes along, a brilliant mathematician, and he presents a different model, a very bizarre model of the atom called the quantum mechanical model. And in the quantum mechanical model, electrons are very, very bizarre. They have what we call a particle-wave duality. In other words, they are sometimes particles like we encounter on a day-to-day basis, but they're sometimes waves, right? And so the model of the atom which emerges from Schrödinger is more of a cloud model like this one. So what Schrödinger said was, you couldn't tell where the electron was. You can only tell what area of the atom had the highest probability of having the electron in it. So he creates these cloud models for the atoms, for the electrons. All right, folks, that wraps up the video on history of the atom. Bring your questions, or the history of the atom, and bring your questions to class, and we'll discuss those next time. Thank you. Bye-bye.